What was it that's most interesting about this conference for you?
Well, it's very interesting just to see all the different experimental focus on various aspects of NMR. What's cool to me to see is that there's an interface of physicists, chemists, and biologists. So it's kind of interesting to see how this focused topic is still bringing such a diverse group of scientists together.
Now, like most of what they're doing is like chemistry based, though, right? It's very like granular. It's very detail oriented. It's kind of tame. It's not that exciting, you know. And then like Mark is bringing to it the whole like gravity modification thing.
Yeah, so I mean, what Mark is bringing is definitely much different than anything else here. I mean, well, experimentally, it's similar in terms of the methodologies and the equipment that's being used, but the application is completely different than other things at this conference.
So that was one of the things that interested me was like it's you know, when you have this big idea, right, it always takes time for people to kind of grok that, digest it, and it's like, okay, so when scientists go home from this today, maybe they'll be like, I don't know, but you know, like tomorrow when they're in their lab, maybe they'll start to attempt some of these experiments.
Yeah, it's definitely possible. Yeah, I mean, there's a mix of people. Some people, they might be able to think things quickly and quickly come to their own conclusion. Other people just have a knee-jerk reaction and don't really think about it, right?
Yeah.
And then others are just open-minded and just don't know what to think of it. So yeah, definitely. I mean, the encouraging thing is that a lot of these people out there have a lot of the equipment that could be used. But what's interesting is Mark is trying to weigh his sample in this, and so he's been going around and telling people, and one of the common questions he's getting is, wait, how are you actually doing that measurement? How are you actually weighing it? Because a lot of these are sophisticated setups where they have a lot of magnetic fields which can interfere with the scales, for instance. So just setting up the experimental device, there's a little trickery just to set it up to get that measurement.
Okay, so there's a lot more that he needs to do then, and that's over time.
Well, yeah, I mean, there's a few aspects. I mean, he did set it up, and so his amplifier blew out, so he collected some data for about 8 hours, and that data, it showed a curious effect where the scale did sense a force. And so now the question is, well, where did that force originate, right? So a lot of people here, they're not thinking about gravity or mass or anything like that. And we're using electromagnetic waves at the end of the day. So I think the real test will be to show, can we rule out electromagnetic forces?
Well, one of the things that you have said and many other people have said is that, I mean, obviously, like gravitation couples to mass in the nucleus of the atom, right? I mean, electrons have a mass, but it's incredibly tiny. It's like 1/1800th of like a proton or neutron. And so whatever is happening with mass seems to be happening in the nucleus.
Yeah.
And so there's this general idea that hasn't really been that focused from what I've seen, right? That, okay, if you're aligning the spins of these nucleuses, maybe it will do something.
Well, maybe there was a talk this morning, just to provide some context. There was one of the presentations where they shared they just figured out the magnetic radius of these nuclei. So what that tells you is, I mean, really where we're at technologically wise, we're starting to just barely understand the magnetic field structure inside of these nuclei. So we don't have a great picture of what is actually happening at that subatomic scale. And so there is a lot of wiggle room with trying to identify, well, what is the final theory that describes, you know, the origin of mass? And there's a certain paradigm that we have right now, but we know that gravity has to be brought in with the standard model. Like, we know that the protons and neutrons are held together with a strong force, and that works great. The quantum mechanics of that works great, but we know that gravity has to kind of play nicely in we know that gravity exists in our universe with those forces, so there has to be some description that no one has a solid consensus on yet. So
yeah. Well, do we know that it moves at the speed of light, or
what's it?
Do we know that gravity moves at the speed of light?
We do have experimental evidence now that gravitational waves move at the speed of light with the LIGO detections, because they have multiple interferometers at different locations, and in order to detect a signal, they actually use triangulation. So they basically try to detect, okay, when did I receive a signal here and when did I receive it there, and they assume that it travels at the speed of light and use that to trigger it, right? Because if there's an earthquake or just a car driving by and it hits one of the sensors, that disturbance won't affect across the planet, right? But if you see some signal in two detectors and they're in completely different states, one's on the East Coast, one's on the West Coast, maybe one's in Europe, then you can say, okay, we detected a signal and it's within this distance that's small. The signals are close enough based on the speed of light. And furthermore, they can figure out the direction at which the gravitational wave came in by comparing all those differences, because if they came in on one angle versus another, it might hit the two detectors at the same time, or there might be a slight delay.
Okay, well, and the reason I asked was, this helps us baseline. I mean, I know that there's a ton, I've seen textbooks that are 3 inches thick on gravity, right?
Yeah.
Now, a lot of those are like descriptions of, they're doing like geometry on, like observational measurements. We see a curvature like this, and here's how the curvature bends. And so it's not getting into like that root level issue. But then at the same time, okay, so we're pretty darn sure that it moves at the speed of light. That's like a bright spot. And the reason I say that is, like, when I got into this back in the 2000s, Tom Van Flanderen had this giant tome that he was pushing on everyone. And his thing was gravitation moves instantly, otherwise the orbit of the Earth would be off, right? But since you can never turn gravity off to check that, I was always like, okay, is this accurate or is this not?
Yeah, I don't know what to think. I mean, well, at this point, we have gravitational waves that are not instantaneous, so.
Okay, so there you go. It's just, science moves forward and we add more evidence, right? And
yeah.
For my part, I saw something just the other day, and it was some new experimental confirmation, and it supported the speed of light. So I'm like, okay, so we know a lot about gravity. There are some coupling issues that we don't know, and then there's stuff like Mond, that's and then that gets more speculative, right? So.
Right, yeah. So I mean, you can have different theories of gravity which might describe different dynamics, but for this experiment that Mark's interested, I think the key is to dive deep into what constitutes mass itself.
Yeah.
So obviously that will come, I mean, you don't really need to know what mass is to have it in a gravitational theory. You just say, hey, I put on a scale, it weighs this much. Now the Earth is this much. If we could weigh planets, we can estimate their masses, determine those, and go from there. But at the end of the day, what Mark is trying to do is what if the mass of a system is actually some dynamical quantity that you can play with? Can you somehow create some creative electromagnetic fields and affect the spins of the nuclei, and would that have an effect on mass? So what's interesting about that is it's somewhat related to gravity, but it's also somewhat independent of the theory of gravity, right? Because two different theories could have different effects for the same masses, but they're still the same masses in some sense. Like it's still the same object, right? Like most people, it's not like a different theory of gravity is telling us more about what makes up the mass of the table necessarily.
Well, this is intensely interesting, and let me thank you again for discussing this with me. I mean, the part that got me was, well, number one, you're doing meta-analysis on multiple different theories, right? And that's something, again, in 20-something years, what I've seen is physicists and engineers, and definitely physicists, right? They all have that model that they fall in love with, mainstream or not, whatever it is. They're like, this is my thing, right? Like John Brandenburg has gem theory, and that's his thing, and no one is going to persuade him otherwise. And he can work in other models. He can obviously work in his part of the standard model, but his brain is always going to go towards gem because that's his baby, But with you, one of the things that blows me away is you've done meta-analysis on all of these different models. And you've done that in the APEC conference where you say, okay, this model describes this model describes that. And then you say, but these three are suggesting this and this other one is suggesting that. And I'm like, that is a whole nother level. So
yeah, I mean, I do believe that most good scientists out there don't get too married to one model, but then they have to decide what they want to research. So they might not be particularly interested in comparing every single theory out there. But if you start studying serious scientists, you'll see that it's not, maybe they're predominantly in one field of research, but a lot of times they're still interested in maybe different systems or even different theories. Even string theorists will sometimes study theories that are inspired by that mathematics, but it's not even string theory. Other times They'll create some toy model and explore those. So yeah, it can really depend. But yeah, I think it is important. At some point, you do have to make these comparisons. And yeah, so some people might focus more on figuring out the details, finding the solutions of one theory, whereas maybe someone else can come in and do a meta-analysis, if you will. So yeah, both are important.
So in terms of manipulating gravity, I guess, which approach do you think is the best? I mean, do you have any insights from the work that you've done?
Well, okay, in terms of manipulating gravity, I mean,
yeah, because
I guess I'm personally interested in these ideas of looking at more exotic differential geometry, because there's been some recent work suggesting that when you look at some of this differential geometry, what may appear to be negative energy might actually be positive energy, just looked at in the incorrect way.
Okay.
And I mean, if you're talking about true gravitational modification, I mean, it's an extremely difficult problem. One way or another, you're going to need tons of energy, but at least with the whole Alcubierre warp drive route, you need a lot of negative energy. So if we can actually realize that there's some theory that is very close to general relativity, matches all of the experimental predictions, yet makes us look at the geometry in a different way and makes us rethink kind of what energy is in a slightly different way, then maybe that will help open doors to figure out how we can actually use tons of energy that we can actually access in our universe to create some exotic technology. And then from there, then we have to figure out how to get enough energy to actually do something that's practical. So there's still a lot of work to be done, but really even in the past 5 years, 3 years, there's been a lot more exploration in the literature. So it's pretty encouraging to see.
Yeah. Well, and the reason I ask is, so you've worked on quantum gravity, right? And you worked at a company that was doing it, or you worked in an organization that was researching that, which is very intense. And that's kind of like a newer, smaller area. And then you've worked on traditional gravity stuff. I mean, you've studied that, right? Obviously, PhD physicist, you've got all of the standard model stuff. You've also done work with Kaluza-Klein, and unified field theories. You've reviewed several of those, right? Like Einstein's, I remember you describing that a little bit to me. So you've got all of these different models. And one of the things that interests me is even if a model isn't right, they could be on the right track, Yeah,
definitely. I always look at it that way. I'm not sure if we'll ever reach the final theory, but what's clear is that each paradigm shift, we get a better approximation. So
yeah,
as a physicist, I'm more focused on what's the theory that I'm not looking for the absolute truth necessarily, but just something that's better than what we currently have that can help us make predictions that are useful.
Well, you said something, actually last night you said something to me that was really interesting. You were like, most physicists simplify gravity. We say, okay, this is a force and it is caused by X, and we're not really sure why, right? It's connected to mass, but that's it. But you were saying, what if there are multiple sources for it? And what that reminds me of is I have read about models of physics that have multiple time dimensions. And so in those models, like, and not being a physicist myself, I'm just kind of guessing, but like, what if there are multiple causal factors for it? So when you said that about gravity, I was like, wow, that's really interesting. And then for me, I went to Mond because at different astronomical distances, it could be that gravity has a different pull, right? And then that would eliminate some of the need for, I think, like dark matter, dark energy that they're postulating right now, I think. So.
Yeah, that's, I mean, you touched on a lot of topics there. I mean, just focusing on extra time dimensions for a second, there's some interesting perspectives there. So there's these particles called tachyons that can move faster than the speed of light, but we haven't experimentally measured these, but in theory you can study them.
Yeah.
They're totally fine in terms of Einstein's relativity. You can make some sense of it. So there has been some work that basically said that there's 3 time dimensions and 1 space dimension for these tachyons, which is a little puzzling to think about what that means intuitively, but there's some mathematics there, and that's interesting. And it was curious because, getting back to what is mass, when we study these different elementary particles, there's 3 generations of particles, and so there's an electron, then there's a muon, and there's a tau, and they all have the same charge, the same electric charge, and then there's 3 generations of quark. They have color charge, but the only thing that distinguishes these 3 generations is their mass. And so one of the one of the things I tried to work on was publishing a paper that looked into extra time dimensions in a very non-controversial way, because one of the issues with a lot of theorists right now is they're unwilling to touch the topic of extra time dimensions. It's just, they can't wrap their head around it. So rather than getting into all these crazy ideas of time travel and this and that, I just looked at it as this higher symmetry that happens to use extra time dimensions mathematically, but it's just trying to describe these different elementary particles that have different mass.
Yeah.
So the different mass states related to the different time dimensions in some sense with what I found. So that's just there's not really a deep engineering application of that yet, but I doubt that many people really pay attention. But you know, if everything went my way, I was hoping that maybe that would allow physicists who are more skeptical of these crazier ideas with extra time dimensions to at least start playing. And what's interesting about that is it's already hinting that there's this notion of a relationship between mass or energy and time. So maybe these extra time dimensions in some sense do relate to mass in some way, which is curious. With the structures I'm looking at, there's kind of the global structure of space-time, and then there are these local structures which get into the higher dimensions. And so I'm not really, with this idea, I tried to make it not too radical, because you still have 4 dimensions of space-time, but then you have these higher gauge symmetries that explore these extra dimensions to kind of, I think of it as unifying energy momentum conservation with charge conservation. So we have these conservation laws, and energy is actually conserved because the laws of physics are the same over time. And momentum is conserved because the laws of physics are the same over space. And so if we have other conservation laws for charge, it actually implies that there's this dimension, this extra dimension that has some symmetry associated with it.
Okay.
But there's 2 ways you can deal with this. You can deal with it globally, like we live in this macroscopic global space-time, but there's a way to play with the math where you get these theories where you leave that alone, but you go locally and you get into the higher dimensions that way. And so there's at least some initial evidence that maybe these extra time dimensions might relate to the origin of mass there. And there actually are games that can be played for extending the higher dimensions globally.
Oh, okay.
One idea is you can basically say that we're always on like a timeline in some sense. So there's a time vector, and we're always pointing in one direction. Like if you want to preserve causality, because the initial confusion, if there's multiple time dimensions, then you could just move all over the place. Like where's the self-consistency of reality? You know, we're used to cause and effect.
Yeah.
And obviously that kind of goes with time. You know, the cause precedes the effect. So you can still explore these extra time dimensions globally. Actually, I worked out the math for this and I took it out of the paper because it was confusing the referees too much. But it works out. Basically, you just collapse it down from the extra time dimensions to basically this timeline that is one-dimensional, and that can rotate and kind of change the direction of time you're moving in. I mean, we don't have good intuition yet for what that means.
Yeah, some of this is kind of like the old flatland experiment, right?
Exactly.
Where when people read physics books, they're at least familiar with that idea. Or Heinlein's Stranger in a Strange Land, the protagonist in that sci-fi book was able to, he was able to tip his enemies into the 5th dimension, which is orthogonal to all the other 4, right?
Right.
So, so I think a lot of people are at least familiar with that idea, but like getting a real grasp on how that would look or work, right? And like string theory, I think loses a lot of people. Brain theory as well, right?
Yeah.
People are like, how could you have this dimension that's curled up inside the Planck length? Well, because it's not in a higher dimensional space, more or less.
Yeah, and I think of it a little bit differently than string theorists, although I study that mathematics. I mean, going back to the ether and this notion, I read this Nature editorial comment where they're saying the reference frame of the ether has nothing to do with a reference frame of space. It has to do with the state of matter itself. So I find that very encouraging because I'm looking into these extra time dimensions and seeing how basically rotations in time seem to affect mass.
Okay.
And so it's really about you're changing your reference frame in time, but it's not like you're changing your frame of reference in space-time. It's more changing matter itself.
Okay.
Which I guess is the goal with what we want to do eventually. It'd be great if we could figure out how to understand these extra dimensions to manipulate matter in our space-time, rather than get lost in this minutia of like, where is this space-time in relation to these extra dimensions? I kind of isolate our 4 dimensions. Like, we always have to come back to that. And so rather than thinking of as extra dimensions of space-time, I almost think of them as extra dimensions to encode matter itself.
Okay. Well, now in I think Einstein's unified field theory, which I think is generally not considered to be correct anymore, right? It's very antiquated. But his solution to connect gravity and the other forces was this metric torsion tensor, right? So he went to spin. Spin was his thing. And if I understand right, Kaluza-Klein uses something like that too, don't they?
Well, so it's interesting because historically, Einstein initially in the early 1920s got very interested in Kaluza-Klein theory. So that started before torsion had been discovered, or at least was communicated. And so the Kaluza-Klein theory idea was to go into 5 dimensions of space-time. And typically in general relativity, you have this metric tensor, which it's just a matrix. So just imagine if you ever had an Excel spreadsheet with 4 rows and 4 columns, it's just 16 numbers. It's just a simple 4x4 Excel spreadsheet. That's all I mean here. And so they have different numbers in there, so be it. And basically, what if we extend it to 5x5 instead of 4x4? And so that is an exact agreement with what I was saying, because the idea is that extra dimension relates to charge. So basically, they were able to get the electromagnetic field. They thought you get this extra vector field and then this extra scalar field in the matrix when you extend it. And basically, they thought that that vector field could represent the electromagnetic potential. But then you have this extra scalar field on the diagonal as well. So it's kind of giving more than you want. And, so that theory Einstein liked that theory for a while. And then eventually, I'm not even exactly sure the reasons, but eventually he kind of moved on from that. And then he had been corresponding with Élie Cartan, who was a famous French mathematician.
Oh, okay.
And he came up with torsion. And so it was a little fortuitous, because Cartan wasn't even thinking of quantum spin or anything like that, but he just happened to be thinking about there should be an angular momentum response to space-time, because energy and momentum and stress is what leads to this space-time curvature. So it's very natural to think about there should be some angular momentum response to space-time. And that's what led Cartan to come up with this space-time torsion, or gravitational torsion. And what's very curious about that is that this is happening in the 1920s, which is when quantum mechanics is taking off. And one of the most amazing thing about quantum mechanics is this notion of intrinsic or quantum spin, which is what this NMR conference is all about. They're trying to affect different spins of matter. So you have different atoms, maybe electrons outside orbiting the nuclei, and they have different quantum spin states. And so Einstein got obsessed with that geometry, and then from there, it's actually funny. So he wrote down this theory of teleparallelism, and there was a letter by Lankos, who wrote back to Einstein saying, this is not a unified field theory because it only contains gravity. So that theory, what's the problem? The problem is it didn't do what Einstein says, but is it a bad theory? Turns out it's a good theory. It's a good theory. It's a perfectly fine theory of gravity. And that theory was rediscovered in 1976.
Okay.
And then that theory became more popular maybe in the past 10 years. And sometimes they don't even cite the 1976 paper. It's almost like it got rediscovered again. They understand it all goes back to Einstein, but it leads to this theory that is equivalent to general relativity, but instead of having curvature, everything is torsion. And when you get into a description of what it is at a topological level, so if you kind of don't get bogged down by the geometric details and all the definitions, but you just look at what the space-time is in some sense, you can kind of see that there's this notion of whether gravitation is curvature or torsion actually is kind of a convention that you're choosing. And this is a deep concept that we're starting to explore in more detail in the past 10 years. And one of the papers that was talking about the positive energy for warp drive was looking at that teleparallel theory, which Einstein originally thought also had electrodynamics, but it turns out it doesn't. So that's pretty fascinating to see how, even though everyone is saying Einstein failed, I mean, people are actively studying this for warp drive applications.
Okay, well, there you go. And just to put a pin in it, also, it comes back to spin, which could potentially, as you've said, that comes back to the DNO conference, that could come back to, Mark's inspiration. Now, with Asilomar, and he'll describe this more in detail, but I mean, with Asilomar, I know that originally came out of measurements. I believe it was the RB47 incident, right, where they documented these measurements with the anomalous phenomena, and the person felt that may have to do with DNO resonances. So, but intrinsically that comes back to spin as well. So,
yeah, exactly. So it's very interesting to then dive deeper and think about, well, what is the origin of mass? To this day, we know that there are these nuclei. We know those are made of quarks, and we know we have electrons, but we still don't have a perfect understanding of the geometry of these elementary particles, these quarks and electrons. So right now, everything is sort of modeled as a point particle, and we just say, oh, there's intrinsic quantum spin. It's hard to conceptualize what that means. It's just go to the math, kind of.
Yeah.
There's not a clear picture. You don't see something actually spinning because it's a point. But other perspectives look at maybe there's some finite size to the object, and but there's multiple ways to even define size. So they'll talk about a charge radius related to electric charge. Now they're looking at a sort of magnetic radius that they're talking about at this conference, which is fascinating. But there's other concepts too, and one of them is called a Cartan radius, which just relates to mass and gravity, and it relates to Cartan's torsion, and it's all connected to spin because the spin of these elementary particles leads to space-time torsion. However, there's no experimental evidence for torsion existing. So people don't, it's this strange topic because it's simultaneously taboo but studied seriously at the same time. So it's in string theory, it's required for loop quantum gravity, and really if you just take an electron and you put it in curved space-time and you just follow the standard quantum field theory or even classical field theory, if you just look at what's going on there, that quantum spin requires torsion for self-consistency and to have angular momentum conservation. And Einstein actually introduced some mathematics in 1928 called the Vierbein or frame field or tetrad. He introduced that the same year that Dirac introduced his electron because he understood the importance of this frame field that is required to discuss electrons with spin in space-time. But we still lack a consensus on whether this torsion is real, even though it's required for mathematical consistencies. So that's one aspect, and maybe it turns out that once we dive into this torsion and we're messing with the spins, I mean, there could be some subtle gravitational effects going on there. So I think a lot more exploration is needed.
Yeah. Well, David, thank you. So what are your other, I mean, if it's okay to ask, what are your other, because you're helping Mark with this and you're working on the Graviflyer, what are the other projects that everybody has their top 10 list. What's your top 10 list?
Yeah, well, in terms of my interest for APEC, I've been really interested in electrodynamics and kind of getting into classical electrodynamics and trying to dive deep. I mean, there's a lot of lore and stories about longitudinal modes really stemming back from Nikola Tesla. So you have this kind of free energy community, and there's a lot of bold claims on the internet, right? But it's a little strange. I mean, when you study these things in school, you might quickly hear this notion of, oh, there's only transverse electromagnetic waves, as if there's no longitudinal. But that's not exactly true. There are longitudinal modes that are in the near zone. So if you have a wavelength of light and you're at a distance that's closer to the source than within a wavelength, you're going to have these longitudinal modes, and that's coming directly out of Maxwell's equations. But then there's claims of signals being sent longitudinally that are traveling over large distances.
Yeah.
So if that is actually possible, then it suggests that there might be some larger theory that describes those modes and allows them to propagate to infinity. And there is a theory that allows for this. And it's been studied by a lot of different researchers. It goes under different names. Some people have called it new electrodynamics. I think Richard Van Duyk, who's presented at APEC, has talked about this. Other people call it generalized Maxwell's equations.
Okay.
So my perspective was to really go back to Maxwell's treatise and look at the work of these pioneers in electrodynamics in the late 1800s and try to see what their perspective was, because Tesla believed in this ether, but that kind of fell out of fashion.
Yeah.
So the idea is basically you can look at the vacuum of space-time as being a material in some sense with material properties. And it turns out when you take that perspective and you combine that perspective with this generalized electrodynamics, then you can study those longitudinal modes as actually being a type of polarization or magnetization of the vacuum itself, which is something that today scholars would say only happens in materials, in macroscopic media.
Okay.
But
then if space-time is viewed somewhat as material, then
right.
Yeah.
Then there's different games you can play. I mean, we know that it has to have certain properties in vacuum when you don't have any strong electromagnetic fields. But the curious thing is that we know that Maxwell's equations should break down. If we take the world's most powerful laser, we're just starting to get to the point where maybe, certainly in the next 5 or 10 years, I'd say, we'll start having more experiments that cross what's called the Schwinger limit.
Okay.
And so what this does is it puts enough energy density such that the quantum interactions with the vacuum become a classical effect.
Okay.
So the ether got banished and it got replaced with this quantum vacuum.
Yeah.
So now we still have classical physics, and then there are these quantum fluctuations occurring around the classical path. And so all of the material-like properties are banished to this quantum realm. But we know for certain that at high energies, really the vacuum is like a medium. The effects change.
Well, so if you shoot an electron that's high enough energy into the void, it will spontaneously create particles, right?
Well, if it's into the void,
I mean,
it will interact with the quantum vacuum with virtual particles, they're called, but you would never be able to measure those.
Okay.
But if you had, I mean, it depends what process you want to look at, but I mean, if sometimes if you have two particles and you scatter them, it gets easier to open doors up. Like if you look at CERN, the Large Hadron Collider, they're colliding two particles, and then that's what kind of opens up all the different, you can create different particles that way.
Yeah.
It's just a little bit easier when you have two things hitting each other to kind of excite all of the possibilities out of the quantum vacuum.
What you're touching on there is like, so Tom Bearden's work, right? Tom Bearden was talking about heavy side and the Maxwell's equations. Tesla, and I've read a bunch of Tesla's original stuff, and yeah, there was a lot. With Bearden, I remember him citing one of Tesla's. It was like an antenna with two poles, very simplistic, right? And basically the idea was you have this waveform that's coming out like ripples in the pond, based on the frequency of your signal, and where those ripples overlap, you get peaks, and
Yeah, so I want to start studying those experiments in more detail now that I have a better understanding of the different theoretical options.
I mean, those were really
fascinating.
And for where you're at, that's really rudimentary stuff too. I mean, that's like grade school stuff compared to what you work with. So
well, I mean, I come from a theoretical background, so in some ways I'm more comfortable with the theory side of things. So I'm still an amateur with the experimental side of things as well. So I mean, there's certain things I can certainly understand about it, but I have to do better.
With scalar waves, longitudinal waves, one of the problems I think is because it fell out of fashion and it ended up kind of being picked up by the alternative, science community, it has kind of been used as this catch-all for everything and anything that basically could fit, like the HARP antenna, right? HARP.
Right.
Nick Begich wrote this book, HARP, Angels Don't Play This One, or something like that.
Right.
And since then, since the 90s, right, people have been like, okay, this is some kind of a scalar antenna that's basically using resonance scalar waves between the ionosphere and the ground to cook our brain waves. Other people have said that maybe it's a communications device for submarines because traditional, penetration of EM doesn't go well in the water. So a bunch of different possibles there,
Yeah, and there was this other claim of some Navy researcher who was able to send these scalar waves through water as well.
Okay.
And that's the puzzling thing. If they can travel over long distances, longer than the wavelength, then something new is happening there. And so it's curious because even from the conventional point of view, we know that really the vacuum is kind of like a medium. Even the text that I studied in graduate school, Classical Electrodynamics by Jackson, I mean, he opens up right away talking about this idea of Maxwell's equations breaking down, and he points out that there is this material interpretation for it. Even though it's not fashionable, it's still there. And the other curious thing, though, is that Schwinger limit, you need the world's most powerful lasers to hit that. So here's the puzzle. Was Tesla able to do something differently that is accessible at lower energies? Maybe is there actually more physics that we don't understand? Maybe we have certain exotic setups with high voltages or high frequencies. Are there other material effects of the vacuum that are still there? I mean, that's one of the things I'm curious about, because we can at least go in with this theory, this generalized electrodynamics. You can even put a parameter on it. And so you could send the parameter 0. When it goes to 0, it's just standard Maxwell's equations.
Okay.
You could change it. And so the history is also interesting because that term was studied in the 1920s by pioneers in quantum mechanics, and they put the parameter in just to get some desirable quantities, and then they took the limit as it went to 0 to kind of remove it. Now it turns out that I don't even believe that it was actually as necessary as they thought it was to get the quantization that they wanted, but fair enough. These were legitimate scientists who studied it, and so some people just set it to 1, other people leave the parameter in, but this is the thing. I mean, it becomes a question for experiment now. What's the simplest experiment that we can find? And that's the problem. A lot of these people don't have the expertise in the theory and the experiment, or maybe they have the experiment set up, but they're trying to sell something. So they don't give you the experimental details, and then they're trying to sell books discussing their theory, which may or may not be right. So yeah, we're just waiting for the right time where enough information can come together where the theory matches the experiment and someone can explain it in simple enough terms that once it's kind of obvious enough, people I think will latch onto it if the data is convincing enough, if there is something to these what these people are doing in the free energy community. I mean, there's a lot of claims and there's a lot of self-consistency in some of the claims, at least in terms of the experimental details. So that's one of the things I'm interested to look further into.
It's a challenge, and that gets into cultural challenges, right? Because I think, with the emerging propulsion community, the anti-gravity, or whatever you might call it, the free energy community, there's this stigma from the mainstream, and then they reciprocate with a siege mentality, right? And so I think that has been traditionally one of the problems, is that even if good work is being done by this or that person, if they're in this community, it doesn't make it out into the mainstream, right? And it's a two-way road. They don't want to share it with the mainstream, and the mainstream doesn't want to accept it. So but
communication is important for science. So
yeah. Well, and then just open-mindedness too, right? Because science changes,
Yeah, I mean, one of the things that Bearden talked about that originally fascinated me was he kept talking about these Whitaker potentials. And so he talked about these scalar wave interferometers. And what's curious to me about that is that we use interferometers to detect gravitational waves. So when we start to look into unification of electrodynamics and gravity, I'm just curious if these Whitaker potentials might be related to some unification with the space-time metric in some way.
Okay.
Because it seems we're at least using, I mean, I don't know if those experimental claims are true, so that, I mean, that's assuming there's something there, though. It's a little curious that they're using the similar types of devices, and that there's a geometric similarity as well. I'm trying to think of a good way to describe this, but I kind of think of it as there's position, there's velocity, and then there's acceleration. Velocity is a change in position over time. Acceleration is a change in velocity over time. And so each is a derivative of the next. And one of the ideas that Einstein played with, not in the teleparallelism, I mean, Einstein tried a lot of ideas for unification. So certainly by the 1940s, possibly by the 1930s, he was playing with adding an aspect of electrodynamics to the metric. And so one of the ideas was to, the metric tensor is usually symmetric. So if we go back to our Excel spreadsheet, basically, if you looked at A2, it's going to be the same as B1. There's going to be this symmetry along the diagonal. So you have 4x4 components. On the diagonal, you have 4, and then there's going to be 6 on the off diagonal, on the upper off diagonal, and then 6 on the lower off diagonal. Those 6 and 6 are the same when it's a symmetric tensor or symmetric matrix. So you have 10 degrees of freedom there. And so what's curious is that if you look at electric and magnetic fields, you have a 3 vector for the electric field and a 3 vector for the magnetic field. That's 6 degrees of freedom. And so one of the ideas that Einstein played with was combining the electric and magnetic fields with the metric itself. Now this one's always puzzled me because it turns out that idea has inspired this Born-Infeld electrodynamics to some degree, and that relates to that nonlinear theory of light above the Schwinger limit that we were talking about. So it does seem that there's some merit to thinking of combining the electric and magnetic field with the metric, but those are force fields, and F equals ma, so it's aligned with, it's kind of like an acceleration.
Yeah.
And if you look a derivative below that, there are these electromagnetic potentials, which Maxwell called the magnetic momentum, and momentum is mass times velocity. So it's like a derivative below the accelerations is the velocities. And so if you look back at Kaluza-Klein theory, they took that electromagnetic potential and tried to extend into higher dimensions and put that vector in with the metric. That was one idea. Another idea was to take the electric and magnetic fields and put it with the metric. That's another idea. And what I realized is these Whitaker potentials, it's not my discovery or anything, but these Whitaker potentials contain the same information as these other Hertz potentials. Now, Hertz introduced these in 1889, and he didn't think they were physical. He just thought it was some mathematical trick, right? But he didn't even think that the electromagnetic potential was physical either. He thought that the electric field and the magnetic field were the physical objects for electrodynamics.
Oh, okay.
But quantum mechanics has showed us now that that is wrong. There's this Aharonov-Bohm effect, and that has established that the electromagnetic potential is the photon field, and that's currently in our current paradigm, that's where all the physics is for electrodynamics. And then you can always derive the electric and magnetic fields from there. But the most obscure are these Hertz and Whitaker potentials, which is kind of like the electromagnetic position. It's a derivative below the electromagnetic potential, and people don't really study this too much. And what's interesting to me is that there's 6 degrees of freedom in the Hertz potentials, just like the electric and magnetic fields. So we can do this idea again, where we can play with this idea of a non-symmetric metric, where we have 16 degrees of freedom, there's 10 degrees of freedom for the space-time metric, and then 6 degrees of freedom for these Hertz potentials. If we add that in, it's kind of a new paradigm to consider for unification. And when you do that, it, at least to some degree with this field theory, looking at it, we haven't specified which theory we're talking about specifically yet, but just looking at the geometry, it seems to start to match what Tom Bearden was claiming with these interferometers, because now he didn't talk about Hertz potentials, he talked about Whitaker potentials, but it's the same information just re-expressed, and it's the same exact data there.
Okay.
And so if we had some unified field that combined electromagnetism with the Hertz potentials with the metric, then you might expect that maybe there should be interferometers used for both. I don't know. And so that's another curiosity.
The man who rediscovered Bearden, the man who made Bearden real. So one of the things that I kind of wondered is, I mean, you are brilliant, right? You know, I know you sound like a kiss-ass saying that. It's true. But then, like, this physics is getting to the point where it's like leaving humanity behind. And so I've wondered if you might be able to leverage like AI. I mean, we already have like the internet and Zoom calls and massive communications to help facilitate physics solutions faster, right? Like, I mean, Einstein, they would write a letter in his day and send it, you know, and
Yeah.
if somebody was like, no, that's wrong, you know, it could be like a month to get a reply back. So we already have that, but then I've wondered if, especially when you get into the depth of models you're in, if like it might be a help to be able to set some of this stuff up, you know, in AI and have it. I doubt that it would come up with like the ultimate solution to this, but you know.
Yeah, I mean, it ultimately depends on how much work you put into it. Certainly neural networks are taking off with AI. Now we have these large language models. So one of the curious things is when you interact with ChatGPT or something, you start to see it picks up on kind of that mainstream consensus, right?
Yeah.
But at the end of the day, that was just a neural network trained on some data. So there's this one process called fine-tuning, and that's, you could take a model that's already complete, but fine-tune it further. You basically feed it more data, and so it gets more domain expertise. And so it's kind of curious because not as many people are talking about this right now, but I'm pretty sure Big Pharma used that stuff to find novel solutions for vaccines during COVID and stuff like that. So there's already precedence of, and it didn't even cost that much money. They spent like $1,000 maybe. So it, depending on how you collect this data, how you train the model, it might cost a little bit of money, but it's totally doable at this point. Let's say you had some strange passion to look back at obscure physics that has kind of been overlooked. If you have all those references, you could fine tune a model that would become a domain expert and connect the dots between all the papers. And that's actually something I've been doing. I've been collecting papers and cataloging it just because I knew I might never read these, but maybe one day I can train AI, because I could see that coming where basically it's going to still pick up everything academia is saying. It's not going to disagree with it. So it's going to be, sometimes it's hard to push the model like ChatGPT and get it to go down some obscure path, right? Even if it's been trained on that data, if it's just a couple of papers, it just kind of gets washed out of the noise. But you could train if you wanted to go in, focus on one. Let's just say you found all of Tesla's patents or whatever, and you found a bunch of information on the internet. You could, in principle, fine-tune a model and see how it does. I mean, I'm sure it would do better than ChatGPT. We don't know exactly how good it could do, but I think a lot of progress could be made in that way. So people who understand how to train AI to go into these niche areas, there's ways to do that. But then there's other ways to use AI to find solutions to problems, often using neural networks now. It doesn't even have to be with large language models, but then that gets probably even more difficult, because then you might have to have a lot of data about the experiment you're trying to set up.
Well, and so ChatGPT, that's going to be doing a lot of paper research, right? I mean, it's going to be reviewing past experiments and stuff like that. And then like some future AI would probably be doing the mathematical modeling, because that's kind of beyond.
We're at the point now where we can, and this was another theme at this conference that was really interesting to see. I mean, really it's already been starting, it's been happening. So for the past 5 years, people have been using AI to find very specific solutions to specific problems. So with ChatGPT, the cool thing about it is it has pretty general knowledge, right? And that's really cool. But it kind of makes sense if you focus on one specific thing, you can kind of, it's easier to kind of get deeper in one topic than it is to get as deep over everything. So let's say you have a very specific problem. I mean, at the end of the day, it's just data in, data out. You're trying to predict something. All physics problems are just trying to predict the future, essentially. Predict something, right? So let's just say you have some exotic experiment and you can change the voltage and the amps, amount of current going in, and you're measuring something, some parameters in the circuit, and you want to see what the output is. So you have some input, you have some output. One way to do it is you just collect a bunch of data, right? If you have enough data, you could eventually have a model that trains and fits that data, just like a large language model was trained to take input text and output text. Now it's just using raw data from physics experiments rather than language.
Yeah.
And so that is already happening right now, which is really fascinating to see. They're talking about it at this NMR conference, which is really curious to see. So it's remarkable how that's taking off. And so I think what'll be interesting to see is how long does it take to kind of bridge that gap between the specifics and the general, right? You could train a model on something very specific, but I don't think we all exactly know how it's going to play out yet in terms of, what's the exact path to get that AGI scientist that can really do amazing things.
Yeah, I think that's one of the most interesting things, is being able to set these things up and have it work on them, because one of the things I've seen is the amount of work that has been done, the amount that's stored in papers, right? And especially when you get into the obscure stuff, it's beyond the limits of human knowledge, and so, it's just at this point where, AI would be able to go through that and collate that. And then it can also do things too, like instantly count references and instantly say, okay, well, there are, 10,000 papers that contain this idea in them, right?
Right.
So, that, for me, that's really interesting. That, and then the other part that would be neat to see is having AI be able to do what they call that game of life simulations, or evolutionary simulations, where you run these things over and over again. And AI would be able to manage those a lot better than a human could. So, for physics models like this, you could put in like Kaluza-Klein, and you could put in, different approaches to it and run variations on those and see what comes out. That would be really neat.
Yeah. I mean, so another aspect of that is generating the data. So there's a few ways you could do that, right? You could have a theory and then write some calculations to compute the solutions and then use that as training data. And the cool thing about that is then you could have experimental data from the real world and synthetic data that you just simulate and mix them together and see where the model goes. So now you're mixing theory and experimental data together and seeing what comes out. So there's a lot of different approaches for how you could look at it.
Yeah, it's incredibly interesting. Well, thank you, man. Thank you for sharing all this. So
appreciate it, Tim.
My brain is fried today.
Yeah.